This meeting is being recorded.
His talk shows exponent conjecture. So, if I want to present Michael Vaughan-Lee, I think there is no need to present him, but I mentioned only 3 or 4 things. The first one, it was presented the second example, and the first explicit example of variety set groups which are not finitely based. Then he did the same 2 examples for Lie algebraic characteristics too. And also, I mentioned something else. There is a conjecture by Vaughan-Lee about the Nagata-Hillman theorem, and he proved this for n equal 4. So the identity is the new exponent 4 implies new exponent plus 10. So, and of course, he's working computers in group theory, etc., etc. So, Michael, and I asked the other to mute their microphones.
Okay, so, well, thank you very much for inviting me to speak at your seminar. This is my first Zoom talk, and it's been a little bit difficult to set things up and echoes and everything, so let's hope it goes all right. You can hear me okay, can you? All right, good. Yes, a thumb is better than a voice because we get an echo whenever you turn your speaker on. So my title is Schur's exponent conjecture. So we better say what that is. So if G is a finite group and you write G as a quotient F over R, where F is a free group, then the Schur multiplier is M of G is R intersected with the derived group of F factored out by the commutator R comma F. And the conjecture is that if G is a finite group with Schur multiplier M of G, then the exponent of the multiplier divides the exponent of G. The usual definition of Schur multiplier is the second homology group H2GZ, but I don't know any homological algebra, and that is absolutely meaningless to me. It's not entirely obvious from the definition that I give that it's invariant, because there are lots of choices for F and R, but the multiplier comes out the same every time, even when you change F and R. And that takes a little bit of proving. I looked up in Wikipedia to see if I could find a proof, but Wikipedia didn't have one. In the old days, you used to go to libraries to find proofs, but now I just go on the web. I eventually found a proof, a nice, short, elegant proof on the web using Stalling's exact sequence, but that was absolutely meaningless to me because, as I said, I don't know homological algebra. I found another proof. Essentially, the problem is if G is F over R and it's also H over S, another presentation, do the 2 versions come out the same? And I did find a proof on the web that said it proved that they came out the same, but I wasn't very convinced by it. Anyway, eventually I came up with my own proof, and I won't go on about that anymore. But if somebody has a nice elementary proof that they could give me, maybe they could email me sometime, because I would like to get that sorted out properly. So what's the history of this problem? Well, Schur introduced Schur multipliers in 1904, so very likely this problem has been around for well over 100 years. It's easy to show that it holds for groups of exponent 2 and exponent 3, but in fact it's been known since 1973 that the conjecture fails for exponent 4. Bayes, Kautsky, and Walmsley found an example of a class 4 group of order 2 to the 68 with exponent 4, where the multiplier mg has exponent 8. But the conjecture has remained open for groups of odd exponent up till now. So as I say, probably for about 100 years or more, open for odd exponent. But I found an example of a finite group with exponent 5, with Schur multiplier of exponent 25, and an example of a finite group with exponent 9 with Schur multiplier of exponent 27. And I'm sure there are lots of other examples, but these things are really quite difficult to compute. I mean, Bayes, Kautsky, and Waumsley example is fairly easy to compute, but even so, you can't do it by hand. You do need a computer, and I think that the reason why this conjecture has remained open so long is that you really need quite high-powered computing power to produce these examples in odd experiment anyway. There's quite a lot of literature about proving that the conjecture holds in special cases, but my view is that most of these results could be described by they fill a much needed gap in the literature. I'd like to take a little bit of time to talk about Waumsley's contribution. It was Waumsley, Bayes, Kautsky, and Waumsley found this example way back in 1973. Waumsley was actually the first person to get the p-quotient algorithm for computing finite p groups to work. And this paper where they found the counterexample to Schur's conjecture was the first significant calculation using the algorithm. And in that paper, they also computed B34, the largest 3-generator group of exponent 4, which has order 2 to the 69 and class 7. Shortly after this calculation, Waumsley actually also gave the first computation of R25, the largest 2-generator group of exponent 5. And that was really pretty significant calculation in those days. Nowadays, it takes less than a fraction of a second on a computer to redo the calculation, but that's with modern computers, and a lot of thought has gone into really slicking up the p-quotient algorithm. But I want to say a little bit more about what Waumsley actually did. If you have a finite p group of order p to the n, then you get what's called a PCP, a power commutator presentation for it, which has n generators A1 up to AN, when the group has order p to the n, and relations when I is bigger than j, AI, AJ is AJ, AI times a whole lot of other stuff, AI plus 1 to the something, dot, 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 up to AN to the something. The asterisks are there to denote exponents in the range 0 up to p minus 1. So for every I bigger than j, you can rewrite it with the I and j in the right order. And then also you get relations AI to the p equals AI plus 1 to the something, dot, 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 up to AN to the something. And this gives actually what is called a rewriting system. And using the relations, you can rewrite any product of the generators AI as a collected word in normal form, A1 to the something, A2 to the something, up to AN to the something. And all the asterisks are exponents in the range 0 up to p minus 1. So you get p to the n normal forms, and that's how you describe the elements of the group. The way you use the relations to, if you've got a product of the generators, to get it into normal form, it's called a collection process. And if it's not in normal form, then it must have a subword AI, AJ, where I is bigger than j, or a subword AI to the p. And then in the collection process, we replace one of these subwords by the right-hand side of the corresponding relation, and then you just keep iterating that. But usually there'll be a choice of which subword to pick. And so there are 3 main strategies that have been used for deciding which non-normal subword to collect. Collection from the right, you scan the word from the right, and the first AI, AJ out of place you come to, that's the one you collect. In collection from the left, you scan from the left and collect the leftmost non-normal subword. In the 1940s, Philip Hall introduced collection for the first time. It was called Hall Collection. Well, I call it Hall Collection. And in this form, you look for a non-normal subword involving A1 and collect that. And if there aren't any of those, you look for one involving A2 and collect that, and so on, and then A3 and so on. And Hall collection is really beautiful theoretically, especially in free groups, but it turns out to be hopeless in P groups. I'll give you an example of the different strategies of collection, how they work out. If you want to collect R259, that's the class 9 quotient of R25. So it's a class 9 group. And if you collect AB to the 5th in that, you can see it takes an awful lot of iterations before you get a normal word. So the time spent in collection is where all the time in computing with the P-quotient algorithm takes. And if you collect from the left, you takes something like 118,000 iterations. If you collect from the right, it's over 2 million. But with Hall collection, it takes over 112 billion iterations before you get a normal word. And as I say, Ian MacDonald was trying to get P-quotient algorithm working with Hall collection. So Walmsley's great insight was that you should use, his insight was to use collection from the right. I don't quite know whether he ever looked at collection from the left. Anyway, he got collection from the right working and managed to then do some significant calculations, whereas MacDonald, using Hall collection, although he did he could only work with very small groups, and so he didn't actually get any significant results. As I say, I'm not quite sure whether or not they looked at collection from the left in those days. Walmsley came up with this idea in 1972, I think. Neubuser at Aachen had already discovered collection from the right. Sometime was good, sometime in the 1960s. But I think Walmsley discovered this independently himself. If you collect AB to the 5th in R25, which is class 12, then those are the numbers. So I never completed Hall collection with that in R25 itself. It just was taking too long. And incidentally, the size of the intermediate words can grow, because if you replace AI, AJ by the right-hand side of that relation, the corresponding relation, it's probably longer. So the words can grow, and with Hall collection in R25, the length of the word got bigger than 7 million. And actually in computers in Walmsley's days, you wouldn't have been able to store it on the computer. They didn't have enough memory. Funny enough, Walmsley, although I think he deserves a lot of credit for getting P-quotient algorithm working, he left mathematics soon after this, and he got into conservation in Australia, and he was really most noted for hating cats. He used to wear a fur hat made out of a cat skin. I'm not quite sure whether he'd shot the cat himself, but he hated cats because of the depredations they caused on Australian wildlife. Anyway, back to Schur's conjecture. Well, I'd never heard of it till last year, and a guy called Vijay Thomas wrote to me saying he was investigating the Schur multipliers of the groups RD5. That's R for restricted, so these are the restricted Burnside groups of exponent 5 on 2 and 3 and 4 generators. And he wanted to know if I knew what the nilpotency class of R45 is. It's known that it has class at most 24, but he said that if in fact the class is less than 24, then he can prove that its Schur multiplier has exponent 5. Seems likely that the class is less than 24, but I don't know what it is, so I really wasn't able to help him. But it got me thinking about this. It was the first I'd heard about Schur's exponent conjecture, so I thought I would see if I could compute the Schur multiplier of R25 to see what the problems with computing these Schur multipliers were. Well, R25, as I say, the largest finite two-generator group of exponent 5. So has order 5 to the 34 in class 12, nilpotency class 12. Now, as a class 12 group, you can get a presentation on two generators A and B with 31 fifth power relations. It's not very hard to find a suitable set of 31 fifth power relations. And so if you let F be the free group of rank 2 generated by A and B, and you let N be the normal closure of this set of fifth powers, then you can get a presentation for R25 as F over R, where R is N times gamma 13 of F, N times the 13th term of the lower central series of F. You've got to enforce nilpotency, because it's my belief, actually, if you only have fifth power relations, the group's probably infinite. And we don't have a proof of that yet. And I don't know whether anybody will manage to prove that. It seems to be an extraordinarily difficult issue, whether B25 is infinite or finite, who knows. So then you get the quotient F factored out by F comma R as the class 13 quotient of this two generator group, A and B, and you make all these fifth powers central. So for U, one of these fifth powers, you add in relations U comma A equals 1 and U comma B equals 1. So that's a group with so 62 relations, 31 choices for U, 62 relations. You can use the nilpotent quotient algorithm in Magma, or in GAP for that matter, to compute this quotient. And then you can read off the Schur multiplier. And it turns out to be elementary abelian of order 31. No great surprise that the 31 is the same as the number of fifth powers needed to define it as a class 12 group. But it's a nice coincidence, and it always seems to work as a coincidence, but we don't have a proof that that's always the case. If you look at the details of the presentation that you get for F over F comma R, then it turns out that if you take the commutator B comma A, its fifth power is actually in gamma 10. So it's a product of commutators of weight at least 10. And that means that if G is any group of exponent 5 with class less than 9, then the multiplier has exponent 5. So this is really important, this, by looking at R25, and it's a central extension F over F comma R of R25, you can see that any counterexample to Schur's conjecture of exponent 5 would have to have class at least 9. And if you look in more detail, it turns out that B comma A to the fifth is a product of commutators in F over F comma R with multiweight R comma S, where R and S are greater than or equal to 5. So it's a product of commutators where there are at least 5 A's and at least 5 B's in every single commutator in the product. I then thought, well, what happens with 7? And this is a bit of a diversion, really. But similarly, in any Schur cover of R27, largest finite two-generator group of exponent 7, B comma A to the 7th is a product of commutators of multiweight RS, where R and S are greater than or equal to 7. And so M of the multiplier, Schur multiplier of R27 is elementary abelian as well. And the similar sort of argument means that any group of exponent 7 with class less than 13 can't possibly be a counterexample to Schur's conjecture. So if you want a counterexample of exponent 7, you've got to be looking at groups with class at least 13, and this is really getting quite heavy calculations. I started looking for a class 9 counterexample of exponent 5. The work I'd done on the Schur multiplier of R25 meant we need to have class at least 9. So let's go for 9 and see what we can find. So suppose we have a class 9 group of exponent 5, write it as a quotient F over R, where F is free. And then we form this central extension H equals F by f comma r. And then from the work on R25, I know that the derived group of h has exponent 25, and that the third term of the lower central series of h has exponent 5. So if you want mg to have exponent 25, then g must satisfy a relation r equals 1, where r is in the derived group, but r isn't in the fifth power of the derived group times gamma 3. Also, R needs to be a product of at least 2 commutators, because it's easy enough to see that if R is a commutator, it's a relation which is a commutator relation, then the order in H is divides the exponent of G. So I've had a look at 2 generators, 3 generators, 4 generators to try and get this to work. And I came to the conclusion you couldn't find any example like this with less than 4 generators. You need a relation which is a product of at least 2 commutators. Well, I'm writing it as a relation, one commutator equals another. So this is eventually what I came up with. 4 generators and single relation b comma a equals d comma c, exponent 5, class 9. And there we go. It turns out to be a counterexample. It's got order 5 to the 4, 1, 2, 2. And the Schur multiplier has exponent 25. And there's the Schur multiplier. I was really chuffed with that. So I emailed George Havas, a great pal of mine, who's also heavily involved in the nilpotent quotient algorithm. And he replied, "You won't know this since you never read anybody else's papers." That's true enough. But your example is the same as the Bayes, Kautsky, Walmsley example in exponent 4. Actually, they tried your exponent 5 example as well, but only up to class 5. So in some sense, I hadn't discovered anything new, but getting it to work for exponent 5 was new. And I'd done the grunt work to show that you really need to go up to class 5, class 9, not up to class 5. And also, to be fair, it's not so easy to get hold of a copy of their paper, because although their paper is reviewed in maths reviews, the maths reviews don't give you access to the paper, which is the way I get hold of a paper. Anyway, I'm not embarrassed about it at all. Lots of maths gets rediscovered all the time. And if you discover it yourself, then you should be pleased with yourself. I also found an exponent 9 example, similar sort of line. So it's 4 generators and the relation BA equals DC, exponent 9, class 9. But to make the calculation be feasible, I put in relations A cubed equals 1, B cubed equals 1, and so on. And then there you've got a group with Schur multiplier of exponent 27. These are big groups. There's no way that Bayes, Kautsky, and Walmsley could have computed groups of this size in the 1970s. And actually, they're stretching the resources of a modern computer as well, as we'll see in a minute. So as I say, these are really quite tricky computations. So my exponent 5 group counterexample has order 5 for 4, 1, 2, 2. And if you work out the P covering group of its class 8 quotient, you've got order 5 for 7044. So you subtract 4, 1, 2, 2 from 7044 and you get 2922. But we've got the relation B comma A equals D comma C, so that takes care of one of those extra relations you need. So you need 2,921 fifth power relations together with this relation B comma A equals D comma C to define G as a class 9 group. It's a little tedious to get it, but anyway, it's not too hard to get a suitable set of 2921 fifth powers. And so you then take a set of relators, all these fifth powers together with the relator, which is B comma A times C comma D. So that's the same as the relation BA equals CD, B equals DC. And then G is the class 9 quotient of ABCD with these relations. And then we want the central extension of that. So we take 4 generators and then we make all these relations in T, relators in T central. So x comma y equals 1 for all these fifth powers, when x runs through all these fifth powers together with the relation BA equals CD, and y runs through the generators of the group. Now, the problem with computing this group is an infinite group because the subgroup A, B, C, D all have infinite order. But the subgroup A to the fifth, generated by A to the fifth, is central and intersects the derived group trivially. So actually you can add in the relation A to the fifth equals 1 without cutting into the Schur multiplier. And similarly, we can add in the relations B to the fifth, C to the fifth, D to the fifth, 1 equals 1. So we now have a finite P group, and we can use the P quotient algorithm to compute it. It's a pretty major computation. It takes about 12 hours of CPU time on my desktop. When I was doing R25, I used the nilpotent quotient algorithm, which can work with infinite groups, but with a little bit of experimentation, you can see that the nilpotent quotient algorithm would have got completely gummed up on a calculation of this size. It probably would have crashed. I didn't actually try it, but even if it hadn't crashed, it would have taken months of CPU time. I have done calculation taking months of CPU time in mind, but if you can do it, you do it quicker than that, it's obviously a good thing. And then I tried the same approach for calculating the Schur multiplier of my group A of exponent 9, but magma crashed. That just shows how much on the edge these calculations are. The magma and gap P quotient algorithms are written in C, but the C is a translation of George Havas's old Fortran code, and I've still got the Fortran code. And so I was able to run this calculation in Fortran, and there wasn't any problem with crashing. I think the magma and gap have C versions of P quotient algorithms sort of inside them, and I think they work fine. But when the group that they produce, they sort of export it to the main magma system and translate it into magma language as opposed to P quotient algorithm language, and that's where it crashed. But that's a technical issue. And Eamon O'Brien is the guy who maintains the P quotient program in Magma, and I asked him about it, and he showed me how to do the calculation in Magma using something called P quotient process, but I won't bore you with the details of that. So these were quite major calculations. But what are the possibilities for other examples? Well, I'm really pleased with this example because, as I said, the two examples I found in exponent 5 and exponent 9 were 4 generators. But here's a 2-generator example. You've got to have a relation which is a product of at least 2 commutators. Well, take A comma B squared, that's a product of 2 commutators to make that a relation. And if you look at the central extension of this group, so exponent 8, 2 generators, exponent 8, class 12, and A comma B squared equals 1. If you look at the central extension of that thing, then A comma B has order 32 in this in that group, and so A comma B squared has order 16, and so that's where the C16 in the multiplier. So that's another 2-group counterexample now in exponent 8. I think there probably is a similar counterexample in exponent 9, but I can't compute that. I've tried up to about class 20, but it's still not a counterexample. I imagine even with the relation a comma b cubed equals 1, an exponent 9 in a finite group, the class is very likely goes up into the 30s. And I imagine if you could compute that far, there'd be a very good chance of getting a counterexample, a two-generator counterexample in exponent 9. Going back to this basic example with 4 generators in this relation, b comma a equals d comma c, you can tweak that with various exponents and various classes. So exponent q and class c, and call that HQC. So the Schur multiplier of H85 has exponent 16. The Schur multiplier of H16.6 has exponent 32, and so on. Obviously, I would expect that goes on forever. H128.9 should have exponent 256, and so on. What other possibilities are there? Well, I'm really pretty sure that the Schur multiplier of H812, so you make it exponent 8 but class 12 on 4 generators. If you look at the central extension of that group, then b comma a has order 32 and d comma c has order 32. But I can't prove that b comma a times c comma d has order 32, and so I'm pretty sure it's true, but the groups are just too big for me to compute. They're just on the edge of what might be possible. And then I imagine that H713 again is a counterexample, but it's just too big to compute with modern computers. There's actually quite a big difficulty because the programs assume that the programs are all working in 32-bit arithmetic. So if you have if you need to address more than 32 bits worth of memory, you get into a bit of trouble. And so the programs would have to be very seriously rewritten to be able to cope with bigger groups than groups of the size of H713, for example. And that's all I've got to say. Thank you.
Okay, thank you very much. It was really very, very nice.
Thank you.
And very, how to say, impressive for me. Do you have any questions or comments?
And everybody's silenced.
I have a couple of comments.
Yes, sure.
When I was a PhD student in Moscow in the 70s, more than 40 years ago, there was a talk at the seminar of algebra about something in computers. And the of Kostrikin were in that time, Americans have good computers, so they good algorithm. Our computers are weak, so we have to be together to have good programs and algorithm. I think in USA you have both good computers and good programs.
Yes, I gave a lecture in Moscow years ago, and reported on George Havas and Mike Newman had computed B44, the largest 4-generator group of exponent 4, and I had a huge, great wodge of fanfold paper. You used to print out these presentations on fanfold computer printout paper, and it was about, so it's a paper, 2 foot by 18 inches, and it was a stack of them an inch high, which had had the presentation for B44 on it. And so I showed them that, and they all clapped. But it wasn't my work, but I was just reporting on the work. On use of computers, Evgeny Kukhro, he provided a counterexample to a theorem of Kostrikhin's using computer calculation. That same trip, I went over to Novosibirsk and met Evgeny, and he told me he was writing this program because he thought there was a mistake in one of Kostrikhin's papers, and sure enough, Evgeny was right. So there were some computations going on in Russia at the time.
Well, 1983 was my first computational conference in Durham, where I met Mike for the first time. And at that time, in Bulgaria, I was writing already some codes. You get a programmer, wait for 2 weeks, then you get this stack with the whole cards, and drop them because they're not numbered. Then your effort is gone. 1983, I saw Chelsea son playing on a computer on the floor. He was probably 3, and I was like, wow. We didn't have personal computers at that time. We just had one big machine in the Institute of Mathematics.
Right.
Programmers. And well, babies were playing in Great Britain with computers already. I was impressed. But it's very nice to see this stuff. I commutate calculations, so it's not easy. I want to know if something about it's not free, is it?
Sorry, I didn't hear that.
Magma.
Oh, Magma. No, you have to pay for Magma, I'm afraid.
Yeah.
Though there is you can go online and log into the Magma website in Sydney, and you can run short programs on an interactive system there for free. But most of these programs are also in GAP, and GAP is free.
Yeah.
I find GAP rather more difficult to use than Magma, I have to say, and it's often.
Well, Magma is Kaylee, right? Magma is the extension of Kaylee.
Kaylee, yes, yes, but GAP often runs a bit slower than Magma. But I did learn how to. I did install GAP quite recently, actually, and I've learned how to use it to a certain extent.
Which version is now? Something like 5, probably.
Sorry?
Yeah. Which version is now? 4, 5?
Oh, 4 point something. Yes, I let keep track of.
What about this peak motion process you mentioned? E.O. Brand explained to you. Is that new? Is that implemented in GAP?
Peak motion process? Yes, that's in GAP. Yeah.
That's in GAP too.
Yeah.
I have a question. You see, in your calculations, you find explicitly the structure of the Schur.
Yeah.
You know the number of factors of.
Sorry, your voice is breaking up a bit.
Okay. Now it's better.
All right, try again.
So then the question is, if you have a complete element of order, for example, 16,
yeah.
I think it's better, or maybe it's better to look at find the exponent of such element without the group computations. Is this possible? to guess the form and to decide to calculate only for this element.
Sorry, I'm afraid your voice is breaking up too much. I couldn't follow that. Zoom isn't always perfect.
Okay, it's better now or noise? Is there any echo?
No, there's no echo.
No.
My question was, if you can guess the form of the element maximal exponent, one element, and you can guess that maybe this works also for other exponents. To check directly only for this element is to determine all the group structure.
Again, sorry, I didn't follow. Did you understand that, Daniela?
No, I didn't.
No.
Okay, I write this in the chat.
Something is wrong with your echo. Mike, I have a question for you. Could you please put your email in the chat? You see where the chat, right?
What, put email where?
In the chat.
I haven't got a chat screen.
So now you go at the bottom of your screen, in the middle, you see chat.
I don't seem to have this screen that you talk about. There's you. I can see you.
Stop sharing the screen, then you will see it.
Stop sharing, yes. Ah, that's better.
Yeah.
Now, if I click on participants or something.
So scroll down in the middle of your screen.
On chat.
Oh yeah.
Click on it.
Chat, right.
Right. And now you can write us your email if you want to.
Oh, I see. Yeah. There we go.
Okay, I asked in the chat with some typos.
That's easy. Just
I see. My question is whether it is possible to check what the exponent of one element is instead of finding the description of the whole Schur multiplier. Yes, it's much. I mean, actually, computing the whole Schur multiplier is not easy. Takes a little bit of underhand methods, I think you should say. Whereas if you just want the order of a particular element, that is quite easy. Yes. Should I type that?
Yeah.
Some noise, I don't know who.
I mean, the reason is you have a presentation for F over F comma R. You can multiply elements. Seems to have doesn't give me enough space. You can multiply elements. Easily enough. but it isn't easy to compute the intersection or meet f prime. See, the Schur multiplier is R meet f prime factored out by f comma r. Actually, computing R meet f prime is not at all easy. But if you have a particular element which you know is in R meet f prime, then it's easy enough to find what its order is. So, yes, guess the form of this element. And in fact, initially, I didn't even try to compute the Schur multiplier. I just worked out the order of this element b comma a times d comma c, and that was enough. As long as that element had order 25, then that was all I needed to know. Did you hear that?
Yeah, sure.
So yes, you're quite right. That in fact, in the paper that I published, I never even said what the Schur multiplier was, because I didn't actually think it was particularly relevant. I only wanted to make sure you've got a counterexample. But a lot of people seem to be interested. Well, what is the Schur multiplier? So I figured it out, but that's much more difficult. I mean, is my screen still shared? Oh no, I stopped sharing it, didn't I? Yes, that's all right. That's fine. So, there, I think probably we've exhausted that. Anyway, thank you very much for inviting me.
Okay, we thank you very much that you agreed to give such an interesting talk.
Yeah. Maybe one small question,
Yeah.
one more small question. You mentioned at the beginning this collection processes, collection from the right, from the left, and whole collection. So these are different reduction processes somehow with respect to the system. But are there maybe some possible completion of this reduction system which will make the process unique? Or this is very difficult? I understand that you kind of, it's very essential that whole reduction, for example, give better results sometimes, or left or right. So, but in principle, I didn't quite understand what are the stars. This is why I cannot say. But in principle, something like completion of initial relations can give you a rewriting system which gives some canonical element. And then it doesn't depend on the process of reduction, whether you use this.
No, you're quite right. I think what you're getting at is there's a thing called confluence of a rewriting.
Yeah. This is what I mean.
That's right. And the idea is that it shouldn't matter if the system is confluent. Then it doesn't matter what order you do the collections in.
So can this initial system
I'm assuming that the group is confluent. I'm assuming that the rewriting system is confluent. Okay, so you get the same answer if you collect from the right as if you collect from the left, or if you collect from Hall using Hall collection. You get the same answer, but it will take longer to do it with
the
Hall
process
collection.
itself.
Yeah. So you want whatever there's a certain number of iterations to do. You have to you rewrite a little non-normal subword AI times AJ, and then you look for another one and you rewrite it, and it's thousands, hundreds of thousands of iterations before you finally get the answer. It doesn't matter which order you do them in, because it is a confluent system. But doing them in one order goes fast, and doing them in another order goes slow. And I mean, actually, those numbers that I gave you, they're slightly bogus in that that's just assuming you carry on rewriting without using the properties of the group. In practice, real live collection algorithms in a finite P group use all sorts of clever information about the structure of the group. I mean, for example, all these generators, A1, A2, they all have what are called weights, which reflect where they are in the lower central series, right? And if in collection from the left, for example, suppose you have a normal word and then you want to multiply it on the right by AI, you'd have, just using collection, you'd have to take it past all the higher AIs one at a time, right? But if the weight of that AI is more than half the nilpotency class of the group, so if that AI is way down the lower central series, then you know without doing it that it commutes with everything that comes after it. So you can actually just slot it straight into place without doing collections. So real life collection algorithms have all sorts of very sophisticated tweaks like that. So in a real life algorithm, the numbers that I was giving wouldn't actually arise because you'd short circuit it. But there are other strategies. I mean, it'd be interesting to know, what if you just randomly picked something? I mean, computer algorithms don't like to do things at random very often, but actually often random is better than...
it's kind of minimal point. Random.
And there's Charles Leadham Green and Leonard Soiker introduced something called deep thought. You know, after the life at the end of the universe, the restaurant at the end of the universe. You remember the restaurant at the end of the universe? It's a book, a series of books about, and one of them involved this big computer called Deep Thought, who was asked the question, what is the life, what are the answers of life, the universe, and everything? And it thought for hundreds of years, and eventually it came up with the answer. And he said, but you're not going to like the answer. The answer is 42. That's the answer to life, the universe, and everything. So that's deep thought. So Charles Leadham Green and Leonard Soiker designed a collection algorithm called deep thought, which says you just stare at the word you're trying to collect and eventually come up with the answer without actually doing anything, just thinking about it.
But also sometimes these clever details put together, they can give something sometimes better. And the fact that they have a weight, I mean the place in lower central series, is it kind of, you really use this in like weights of the variables, or it is only this only in this argument kind of that?
Sorry, I missed that.
You said that these variables have weights which are kind of defined by place in the lower central series.
Yes, that's right.
So then kind of you have a graded rewriting system.
Yes, it is, yes.
So
I mean,
it is...
if you have a group of order p to the n, you know it's nilpotent. Let's just... and you go down the lower central series in steps, and then you refine the lower central series by putting steps p at a time. So you end up with a central series with p steps in it. I'm sorry, n steps, where n is p to the n is the order of the group. And then those generators are, the generators A1 up to AN generate these steps, these cyclic steps. So it's graded. If it was a Lie algebra, you would call it a graded Lie algebra.
I mean,
yes.
It might be can be used for something else, not only that.
Certainly, I mean, when you're working with nilpotent groups, you use the fact that, gamma I comma gamma j is contained in gamma I plus j. So you have a, a group.
Yeah.
Right, yeah. And that's exploited a lot. Yeah.
Some other questions?
Yeah.
Or comments?
Yeah, I'm well outside group theory and algebra in general, but in verification, there are sophisticated data structures which allow symmetry to be reduced a lot and really huge state spaces to be exploited. And you mentioned you coded something from scratch in Fortran, and you did better than Magma, which either means that you used such structures too, or that Magma doesn't have it.
Actually, no. The Magma code is actually C code. I mean,
yeah, there are libraries, packages for C for this.
And the C P quotient algorithm in Magma is translated from Fortran, George Havers's Fortran stuff. So originally P quotient was written, I don't know what language Vaughan-Lee was using, but soon after that, a guy called my friend George Havers wrote the P quotient algorithm in 70,000 lines of Fortran. And that was the standard for quite a while. And then Eamon O'Brien translated that into C, and it's Eamon O'Brien's version that is inside Magma. But the problem was that Magma crashed because although Eamon O'Brien's code didn't crash, Magma needed to interpret the results from Eamon O'Brien's code, and somehow in taking the internal version of the group inside the P quotient program and translating, extracting it so Magma could know what it was, Magma crashed at that point. So I just went back to the original Fortran code from which Eamon had got the C code. So I didn't rewrite it. I didn't write it. I mean, but I'm intimately, I'm easier. I do program C, but not very much. And I'm better programming Fortran.
I'm talking structures in which you never spend a fixed amount of, say, memory on each, say, explicit element of the group. You just describe them in terms of sets of elements which you multiply together by just conditions on those sets. And this works for transition systems, saves an awful lot of space and time. And it's called symbolic model checking. In Sydney, I think in Australia, they are experts in this, just like elsewhere. In Britain, I worked for a group which...
Well, it's certainly true that to get some of these bigger groups that I'm interested in, one needs to rethink the whole program needs to be rethought and store the information more efficiently or whatever. At the moment, the code just has one big array, and the biggest I can make that array inside Fortran is 2.4 billion.
4 gigabytes. Yes.
Yeah. So,
okay, I think that there is a general principle that some of the computers, they are user-friendly and some are computer-friendly. And the sum of the two friendships is a constant.
Yeah.
So if you want the program to work fast, you should use computer program which is not so user-friendly. For example, if you use this code with 0 and 1 only, this is the best way to write the program. From the point of view of the speed of the performance. But of course, this is not so friendly. And for Kant, this is a language which is not so friendly, but is faster than some other things. So, had this experience, we have to multiply 5 by 5 matrices, and if you with C++, and if you write a cycle, this is 10 or 20 times slower instead to write these 25 products.
Yeah, this is called program specialization. And some time ago in the Journal of Automated Reasoning, somebody spent several pages to show what the specialized version of a loop looked like, just to dissuade, to put off the audience from reckless specialization. When say a loop of 100 iterations is converted into 100 lines of repetitions of the body, yes, and it is still specialization. And it saves some time, because time is saved on updating the counter, but it's now 100 times longer. The code I'm talking. Okay, so there is a lot about that. Yeah.
I think today we had something like a seminar which was really that all we presented in the same place, not by Zoom and by this one, because many people, they think that the good part of the seminar is not only the talk, but the possibility to discuss the things before and after the talk and during the talk.
Sure.
Today we had this. Okay, Michael, thank you very much.
Thank you.
Shall I stop recording now? I'm
Jolly
stopping
good.
recording.
Okay.
All right.